right, we'll go ahead and get started. Thanks everyone for joining. I'm Brian Hale on the incubator team. I think I know most of you. I'm very excited to welcome Kim Chi virtually to AI2. I think he's well known to a number of people around AI2. I'm the lucky one that gets to make the intro. Gur and I were reconnected over the summer as he was on the tail end of a very successful tenure at Amazon. Turns out we'd actually met a few years earlier. We didn't make the connection. I think now I realized we had made axes together in the desert, which is a totally different story for another time. If any of you have know Gur or you've read his bio, you'll know he's seen a lot, from startups to big companies, networking, robotics, software, federal regulations, which I'm guessing we might hear a little bit about here today. You name it. And as I alluded to, Gur recently left Amazon after a very successful tenure where he most recently helped launch and deliver Amazon Prime Air, which will be covered a little bit today. And again, I just want to reiterate, Gur, welcome to AI2, or welcome back. I know you've been here before, and just thanks so much for spending a little bit of time with us.
Yeah, of course. Thank you. And this is going to be sort of a semi-interactive presentation. We're going to keep time a few minutes in the end for questions and answers. I do want to get to the end of it. So if you have a burning question, then ask. But if you don't, just write it down, and we'll get absolutely will answer as many of them as I can. And I think there's time for one-on-ones later on if people want it, if you think that's helpful. I know I'd love to talk to some people, and I find the research that you're doing at AI2 fascinating. So that'll be good for me too. So I'll just launch into it. This is me. I usually show the before and after in Primer, right? The 7-year round. The main difference, I think, for me is the less hair part. At some point, I realized that these big projects, you feed them with hell. At least that's history will show. But that's the product we produce. This is from sort of an event we've done last year, or sort of we being Amazon when I was still there. I'm no longer related to Amazon. I'm my own person now. And that device next to me is the Mark 27. And we'll talk just a tiny bit about it. I'm happy to talk about it in the future. This really isn't about it. It's just more of some lessons that I've applied along the way, because this was an aerospace program that I always felt that they fit in other domains, especially AI and robotics. And this is really what I'd like to talk about today. Personally, I'm interested in system of systems, especially when you try to hit these extreme scales. There are a lot of problems that are when each individual system by itself and the scale is low are tractable, and they sort of go out of control and they run away from us in terms of side effects and certification and sort of edge cases, if you will, as you make them more complex in terms of the number of systems they interact and the scale they operate. I also find myself gravitating over my life into problems that are more about manipulating atoms as opposed to manipulating electrons. Clearly, you have to manipulate electrons of computational information theory, etc. But I just find that problems that are purely on the electron side are sort of solved to the most part, not completely, but to the most part. I mean, we can throw more memory, more CPU, more networking at the problem, more data, and things tend to get better or easier, maybe not across domains, but in certain domains, definitely. And things that relate to the real world, and you have inertia and heat and safety and etc. They're just not naturally harder. And then sort of I also found myself over the last, I would say 20 years, thinking a lot about AI and how to bound the failure cases of AI. And I've done projects of in telecom, in sort of at Microsoft when I worked there on some AI systems, and of course most recently in aerospace for Amazon. So also deeply interested in coffee. If you ever want to talk about it, we can geek to no end at all. So we'll talk today is a conversation about Swiss cheese. Quick question, like you don't have to answer, but it'll be interesting how many people actually heard about the Swiss cheese model before. Because I find that there's a lot of variability. I mean, people who ever worked in either the medical space or the aerospace domain, especially on the design side and system engineering side, will tend to know about the Swiss cheese. People who worked outside these domains don't really know much about it. And I think there are lessons learned from these other industries. Michael says, I have not heard it before. Excellent. So at least one new person will know about the Swiss cheese. I'm happy to say that I've been talking about the Swiss cheese all my life. I grew up in an aviation family. My father is a pilot and builder of experimental airplanes, and in his retirement now, he's being retired from being a commercial pilot. He's a airline and aeroplane incident investigator. So his life is all about the Swiss cheese, and he actually teaches it professionally. And I got to sit in some presentations that he done to other pilots when I was a kid and hear about it. So I sort of grew up in this with this mental model in my head. It was sort of a lot of fun to see how you can apply to different domains. So I would say the switch model is not new. I found a graphics that simply by looking at the fonts and the quality of graphics can tell you how old this is. But the idea is really, really simple, right? Accidents in complex systems, or incidents, you can call them, are generally, they have a sort of a comorbidity factor, right? I mean, we can talk about comorbidity in other domains, but it's very uncommon that the accident is caused by a singular error. Usually there are a lot of things that have to go wrong, and somehow that combination of errors magically manages to have all the holes in the Swiss cheese perfectly aligned in order to actually result in something that is dangerous or damaging. And I think that's a key point, right? Because it tells you two things. One, it tells you that you often have to think about an error as this compound comorbidity error, number one. Number two is, as you add more layers of protection in your system, you need to make sure your holes don't align. And we'll talk about some examples of what that means for robotics in a second. But I want to maybe stay in aerospace just for a second. Here's a way that most aerospace companies will think about a risk factor, right? So you think about the Swiss cheese and how the Swiss cheese will hit you. You try to think about a combination of likelihood of something happening and the severity of that thing happening, what will actually cause. So let's just do a few examples. So, if you ever flew in a commercial airplane and you visit the pilots, you recognize something interesting. The pilots never eat the same food on the plane. Because if the food is contaminated or poisoned, let's take the terrible example, right? At least one of them will be safe, right? So by definition, they don't eat the same meal. So that's the regulations. So let's say they forgot. Let's say they didn't pay attention. Both the pilots eat the same meal. They both get incapacitated, right? Then the Hollywood scene where the stewardess jumps to the middle of the plane and goes, is there a pilot right on board that can help save us? Now, that's extremely unlikely. It never actually happened outside Hollywood. But of course, it could, if you sort of look at that matrix on the right, if it happened, it actually would be terrible. But it doesn't happen, right? Because it's extremely unlikely. But that's an example of a failure mode that you solve by multiple layers of the cheese. You make sure that they don't have the same food. You make sure the people who give them the food ask one and then guarantee that there's a mutex, that then ask the next person. And there's a little protocol, by the way, that pilots do in a cockpit when they get their lunch or dinner or whatever. One of them will say, you pick, because remember, it's the chicken or beef. So one of them say, you pick today, and they pick the chicken, and the other one will eat whatever the other food is, which is sort of interesting, right? So there's a protocol that protects us. There's another example, which is the other dimension. It's not extremely unlikely. It's certain, right, that if you have a multi-engine aircraft, one engine at some point will fail. That's why you have more than one. But the flip side is insignificant because of the design engineering that went into airplanes today. There's something called ETOPS, which is extended twin operations, which means that you can fly for more than 30 minutes or an hour with just one engine, lovingly called by pilots engines turn or passengers swim. That's the sort of the funny acronym. But it's true, right? I mean, when you take a twin-engine airplane, a 777 or 737 or one of the Airbus 350, and you fly over the Atlantic, over the Pacific, that airplane is ETOPS certified. It has certain engineering, testability, certification, and currency requirements. Each of these represents a layer of the Swiss cheese that guarantee that if you lose one of these engines along the route, you can safely complete the flight. And the reason for this is, unlike the first case, where it's extremely unlikely that both pilots will be incapacitated at the same time, we know it's almost certain that you will lose one of your engines. So we just don't know when it'll happen, right? So now you sort of do something about it. There are other examples, right? So the miracle on the Hudson, I'm sure everybody heard about it. You fly into a flock of birds, one layer of the Swiss cheese, right? Generally, that doesn't happen very often. You lose both engines. That's incredibly unlikely. Right? That's in that extremely unlikely common. But the next layer of the Swiss cheese happened. Both pilots were trained and current, and they managed to successfully ditch. So it ended up being a major incident with some people being injured, but nobody died. And that's really, the ideal outcome out of something like this. It's not unlikely, it's extremely unlikely, but it did happen. And then the final layer of the Swiss cheese, which you have excellent pilots that are ready to handle that anomaly, or an operator, were available. But what if you don't understand the failure mode enough, right? What if you think the failure modes are robust, you understand of them, but they're actually fragile? And what if you don't have enough layers of the cheese? And this is where actually something really important happens. Often, we as humans are really bad at estimating small numbers, these remote probabilities. And this is actually one of the biggest problems as systems get more and more complex, that very few people have an understanding, an end-to-end understanding of how they work. And unless you have a really robust simulation and testability framework, it's very hard to know that how to map these failure modes. Are really extremely unlikely, or will they probably occur? And if they're extremely unlikely, sort of the age of the universe, etc., then your mitigation is purely statistical. But if they will probably occur, then you need more layers of the Swiss cheese. So that's okay. But what if you don't have enough layers of Swiss cheese? And I think we know at least one Seattle-based airplane company that made exactly this mistake. It ended up being, they underestimated the fragility of the failure modes, and they didn't enough Swiss cheese, and that's the 737 MAX issue. Now, there's a lot more complexity in it that relates to every part of the system and pilot training, etc. But at a high level, this is sort of part of the problem. Okay, so this was very aerospace specific, and you'd ask, like, is the Swiss cheese used in other domains? And the answer is absolutely. Here's a sort of a picture I found online. Thank you, Google. And it's really about sort of how Swiss cheese is used in making sure people don't get dangerous medications, something that will actually harm them. And it's the same idea, right? You have systemic layers, and each of the layers have to sort of, the combination of all of them make sure that these errors don't happen very often, or never, right? I mean, it's all probabilities and you play the game, but you need to make sure that there are no common failure modes. That's sort of one of the, in other words, from a Swiss cheese perspective, the holes do not align. That's sort of the way I'd like you to think about it. So going back to sort of how we think about AI and robotics, right? We have a huge amount of complex machinery. We often sort of are, I call it expert practitioners as opposed to inventors. We may make modifications to a part of the system, but we generally use a lot of other parts, open source, whatever frameworks that are available, either commercial or otherwise. And we build a system of systems. And there's a lot of, the complexity is a lot of these sort of probabilistic systems that interact in what we hope to be a closed form way, but often, how do we guarantee that these behaviors really, truly are closed form? And we tend to spend the bulk of our time understanding how a system works. And then the sort of what is the functional requirements of the system, and does it deliver against the functional requirement? But we really should spend a lot more time on how a system could fail and will fail. Goes back to sort of the what could happen, what will you do about it? Do you have some protections? Now, the key question is sort of, are these failures benign, right? I mean, if you have completely benign side effects, who cares, right? And again, think about that severity versus likelihood way of sort of a matrix. That's one way to think about the benign. So let's just pick completely benign failure, right? If Google gave me one wrong link out of 10 blue links for Grumpy Cat, nobody will care, right? I mean, it could be a failure. It can be a failure that happens on every single Grumpy Cat query. I have not done the statistics. I'm sure someone would love to do it. But who cares, right? It's completely benign. But some failures are really not benign. I'll go all the way to the other extreme. So this actually is what $100 million looks like when it hits the moon at 2,200 miles per hour, which is the Israeli Space IL, I think was the name of the team. That's the first privately funded spaceship that tried to land on the moon. Of course, they failed. Why they failed is something we'll speak about later. Actually, I know one of the system engineers and testers on that team, very, very, very talented individual. And she should help me understand sort of exactly the failure model. But this is a classic example where they had a lot of protections, but they underestimated the human factors impact of how humans can actually screw with the failure modes, end up sort of failing for a completely unnecessary reason, right? The holes align in a way that they did not expect and did not protect against. And let's just think about some few design decisions you can do actually in robotics. Let's step away from aerospace for a second. The first is we often talk about redundancy versus diversity. So here are 3 sensors. I assume you recognize them: camera, sonar, bolometer. One of the advantages, of course, of each of these is that they have a different physical sensing modality. They interact, they perceive the world in a different way. And then the question is sort of which configuration, I'm going to show you 2 configurations, is more reliable. And of course, you have to define reliable. Always it's critical to define your terms. I'm going to define reliable in this case as able to recognize objects that we must miss. It's a robot, it's moving around the world, it needs to detect things that it can touch. Okay, so here's configuration number 1, 3 cameras. Here's configuration number 2, a camera, a sonar, and a bolometer. And the question is, which one of them is more reliable? And here's an example view. If you're a computer vision scientist, you know that surfaces that are mirrored, especially if they're really good mirrors, are basically, the computer vision algorithm, if you're doing photogrammetry or whatever, will happily reconstruct the geometry and detect objects in there. And it's extremely hard, especially unless you have a lot of extrinsic sensing, to understand what's going on. And is the world deeper than it is, or is there a structure there? And can I avoid the building just with a camera? And the answer is that's actually really, really hard. But what if you don't have a camera? If you have a sonar, that window surface will reflect just fine. And that's great, right? Here's another example. This is a bolometer example. So I think this is in Spain somewhere, and the temperature of the sand happens to be 37 degrees centigrade, and that's also close to the temperature of humans. So if you have a bolometer and you hope to be able to detect humans, that's going to be, they're invisible. They just became stealth. And here is my dog and cat. So it's a cute picture. Must put a cute cat picture on any presentation. And if you try to detect them with sonar, it turns out that the fare of a lot of pets is stealthy in sonar. It captures there are no reflections, and they're just invisible. So the only way to sort of make sense of this kind of a universe that where you have to miss the dogs and the cats and miss the mirrors and find the people very reliably is if you have a diversity and redundancy, right? That's really important. So the question that I generally ask in sort of in the Swiss cheese arguments is that you have a fail dissimilar, a fail operational, fail safe design patterns in your system. And fail dissimilar means that the 2 failure modes, so the failure mode of a sonar, a failure mode of a bolometer, are going to be physically different and distinct, right? So they don't fail the same way. And if you have 3 of them, then you can fail in an operational way. 2 of them may be sufficient. Right? If you fail to just 1, then you end up with a dangerous design. But you have 3, you fail to 2, you feel that you can still be operational. You also need to recognize when you fail down to just 1, potentially, and then put yourself in a fail-safe mode. Well, I probably shouldn't continue to move around. I should self-arrest and ask for help and basically stop myself from doing anything because I can't really perceive the world in a safe way. Another example, here's a classic system interconnect in a data center. Right, so generally what you do is you have 2 Ethernet, or sometimes 2 internets plus a light outs management serial network, and that's how you have redundancy to access your network. But there is something pretty important here. There's a common failure mode, right? If you're connected with 2 Ethernet switch networks, Ethernet is your common failure mode. If someone is attacking the Ethernet protocol, they can attack both sides with the same methodology. So that's not as robust if you connect using completely different technologies. Right, let's say you do CAN bus, Wi-Fi, and Ethernet, and you can fail between these 2 modalities. A single attack won't be able to take all 3 of them easily. You now need a much more complex failure or much more complex attack. And it's actually something that you see in modern airplanes when you do fly-by-light, where you have a combination of fly-by-wire, fly-by-light. In other words, you have some fiber optics, then you have some actual sort of communication system, sort of like Ethernet and CAN bus to the most part. And the idea is that that system will end up being more robust. Another example is between simplex and complex, and then you can think about what that means for redundancy and diversity. This language won't make sense. So I'm going to show you 2 airplanes. One is a single engine airplane, one's in twin, and I'll ask you sort of which one is safer. And again, remember the definition of safer. So here's the first airplane. That's a Cessna Caravan. It's an extremely popular airplane around the world. It's a jet engine, turboprop technically, but still a jet, very, very reliable. And here's a King Air, and that has 2 of these engines, right? So twice as many reliabilities. Potentially, you can absolutely design to lose an engine, and keep flying and get you down to the ground. Right? That's the big selling point of an aeroplane like that. It's just an overall better airplane if you want to fly passengers. So here's, I'm just going to let you read this text. And then I'll ask you, in your head, which one did you think was safer based on your sort of being just a customer of flying airplanes and knowing airplanes and understanding technology and failure modes? And which one was safer? And this just look at the highlight, right? So it turns out that if you run the statistics, the single engine aircraft is 4 times safer for the occupants than a twin, which is completely unintuitive, right? I mean, sometimes a simplex solution is safer than a complex solution because the failure modes are much more benign, more benign. Now, you'd think that the world will move to single engines as a result. This study was published in 1973 by the NTSB. Okay, that's almost 50 years, and here we are, and we still believe multiple engine aircraft are more reliable than single. This is actually not probabilistically true. It's just that we as humans feel more comfortable when we see multiple engines. They're actually riskier. And that may be frustrating, but like psychological elements are really, really important. So I got to sort of leverage the Swiss really extensively in my last project. This is sort of that aircraft again. It's a cute animation of it. And one of the things that I insisted, again, just because I have that experience in safety critical engineering from other projects and also growing up, building airplanes and flying airplanes with my father, is that we only spend about 30% of our work or our time on the functional part of the system, making sure it can deliver the functional elements. Fly, be able to sort of, get from A to B, et cetera, et cetera. 70% of the work was on protecting the system from the world and protecting the world from the system. And it's literally sort of, you can think about the entirety of that project, and it was 30-70. And I would, if anything, I think is less than 30 and more than 70 if I actually look at the sum of all the work that we invested over the years. And that's unusual because I get to talk to a lot of teams, and they generally will think about, well, we now have the functional stuff ready, we can go test it. But it's actually, if you have a safety critical system or a system where you can bound the side effects and they may actually cause some harm, you have to spend a lot of time thinking about how to protect the system and how to protect the world from the system early on, and that actually is the most of the work you're going to have to do. And if you push it out to later and you haven't paid these taxes along the development timeline, you're not going to have a product that you can actually trust. And again, if you're doing Grand Piquet, maybe that's okay. If you're doing anything more complex that interacts with the world, that's not going to be okay. So one of the ways I tend to think about it, this is again very aerospace specific, but medical systems and communication systems also use this concept. Is a concept of operations. So here's the one for prime air, just to use one that I'm going to sort of pick an example out of later. So you take it from a fulfillment center. Once you get an order, you fly, you transition into an aeroplane mode. You fly towards your destination. You detect objects in the real world that you can talk to. Most of the time, you can talk to other robots and other airplanes. Some of them you can't, and you detect them and then avoid them. You transition back to the delivery area. You find where you have to deliver the package. You survey the environment. You do perception yet again, different kind of perception. You have special treatment for people and animals because they're just unique. Right? If you have to ditch, you want to make it's okay to ditch on a tree. It's not okay to ditch close to people. And then you eventually deliver the package. All right. Long story short, let's just deep dive on one building block, which is the simplest one. The first thing you have to do is take off. And to take off, you need to know that the area above you is clear, and the algorithm and the system or the building block we've built for this is called the climb path clear building block, and it actually has multiple sensing modalities and multiple algorithms. Let me sort of give the example. So the first is algorithmic diversity. So this is a CNN-based algorithm, training-based, massive amount of training data, massive amount of sort of ground truth, etc. And the idea is sort of if I have to sort of fly through this flock of birds, where is the safe area around it? And this is sort of pretty simplified version of it because it doesn't have the dynamics of the aircraft or dynamics of the bird's model, because obviously if I fly behind the bird or in front of the bird, the dynamics are very different. And here's a sort of a more complex version that actually has a little bit of dynamics. This one looks up. It's actually the sensor package carried by one of our scientists while he was skiing, I think. And again, the idea here is sort of do you have high confidence and of where the aircraft, can the aircraft take off and where can it take off? And this is a continuous algorithm. It runs all the time. So the algorithm needs to continuously tell the system, there is a safe path to climb, and here is what it is. Okay, and there's another kind of family of algorithms. I'm sort of showing this all combined. On the bottom left, you have a photogrammatical algorithm using stereo. And on the right, you have these deep neural networks. On the top right, what you're actually seeing is the decision, the vote that both these sensor modalities and both these algorithms made. And they basically said, is there a valid path? And right now you see that you notice sort of the squares sometimes go red, depends if there's a valid path or not. One of the things you notice that if you look at the bottom right now, you notice that the sun just went into a sort of red. It basically said, we don't have information about the sun. And this is important because it's actually a tri-state decision. I have data, I can tell you it's safe, is state number one. I have data which shows that this is not safe, is state number two. I don't have data, therefore I can tell you it's safe, therefore it's not safe, is state number three. And I often see people sort of miss that third state, right? I don't have data also needs a first-class treatment as part of it. Okay, so of course, the trick here is both the photogrammatic and the neural network algorithms must continuously agree that there is a safe path for the aircraft to continue to climb continuously on every, like all the time. But then you add some physical diversity into it. So here's a sort of a computer vision-based algorithm that does human detection. This is a daughter of one of the primary team members playing soccer. And it's actual sensor package, and so the classifier is trying to say, is there a person close to the delivery area? And in other words, is the delivery area safe to get close to? What's interesting, a shift here is exactly the same scene, but not captured with a long wave IR sensor. And a completely different algorithm was optimized to work on bolometry. And if you ever done sort of CV work on bolometry, you know that it's just different and complicated in unique ways. But the idea is that you have two different sensors, two different algorithms, and they all have to agree that there is no human in the delivery area or to proceed with the mission. So really now the model is that you have multiple fairly similar algorithms running on data from multiple physically dissimilar sensors, and everything has to agree it is safe to proceed. Otherwise, there is some predictable treatment around don't proceed, do something else. And in other words, there are layers of the cheese, right? So specifically, if you think about the primary program, we designed it with 5 layers of cheese. Number one, you manage the available space in 4D, 4D both space and time. Then you do strategic coordination, which is at the time when the mission is flown, and you do tactical coordination, which is peer-to-peer, doesn't use any infrastructure, but it's still communication-based. And then you have some sense and avoid around just understanding the geometry of the world and what's occupied. And then you have a special treatment for humans, where you said, well, I don't actually care about the geometry of the world. I actually care about where are humans in the world. And if I'm forced to ditch, let's say, I'm going to ditch on a tree and not close to a human. And of course, the idea is to make sure for a complex sort of requirements, traceability, verification, validation, that the holes, the defects in each of these layers of the cheese do not align. And that's a massive testing campaign, obviously. So the question is, what is your approach to training and testing, right? I mean, I think there are a lot of robotics applications these days that are, I call them the McDonald's model. We collected over 9 billion road miles, and every time we see a defect, we'll go back and the engineers will fix it, and eventually we'll run out of defects, and the system will be sort of great, and it can sort of react correctly to almost everything that you see in the world. And again, this is how I think about it, and that makes me uncomfortable, because sort of one of the lessons I've learned over 30 years of building these kind of systems is the world is absolutely amazing at producing random events. Think about this, the ultimate random event generator. And the key question that we have as sort of AIs, engineers, and roboticists and expert practitioners is, will our system behave correctly? And I'm saying correctly in the context of safety, when it's presented with a completely new event, one that is never ever seen before. And it's clearly sort of new events. If you're a Taleb reader than black swans. I actually spoke about this recently with someone who's from Australia, and he reminded me that Australia is only black swans. For him, it's the one white swan example. But the key to think about is like, what if each of these events happen exactly once? And I'm talking sort of in a transactional sense where they never repeat. So if the things that you observe in the world happen exactly once, never repeat, how do you train against them? What does training even mean? Because you accumulate a lot of training data that you'll never see again. That actually makes your system weaker, not stronger. So, and how do you test against a system that needs to sort of survive in such an environment, right? And again, survive means have safe outcomes. So here's my view of the world. My view of the world is full of black swans, and we just have to deal with it. And your system design, engineering, testability, verification, validation, certification, whatever you do, has to accommodate the fact that the world will continue to throw these random events at you at a power law kind of distribution. And the specific solution I did in Primal, this is not the only way to do it, but it's the one I've been using for a few projects, in my life. Is zero-day testing. So the way we interpret this in Primal is there are two key metrics. One is called alpha, and the other one is beta. Alpha is the chance of the mission proceeding when it is unsafe to proceed, right? So that's a safety violation. The system failed to detect an unsafe state, right? That think about looking up and making sure that there's nothing above us when we climb. We missed something, and therefore we proceeded. And beta is the reverse. Beta is we saw something that wasn't there, and we aborted when it's safe to proceed. And now, when you have two metrics, you optimize them differently. And of course, the goal for Primal was to make alpha incredibly small, never ever have a safety mistake. But it means that I can't make beta as small. Beta has to be bigger, which once in a while I'll abort a mission that I don't need to. That's okay, because I'll never proceed with a mission where I shouldn't. And that decision is sort of the foundational when you build systems that are safety critical. But how do you know it works in the real world, right? So generally, you work a lot with data and scenarios, and these are something technically called level 2 scenarios, so the end-to-end system simulations. And let's just look at it. So here's a simulation. This is sort of the aircraft is trying to deliver. Let me see if I can play the video. It'll work very, very slowly, but you can see the aircraft descending. And if I move the mouse a little bit, where my mouse is showing right now is a dog, right? So the dog is too close to the marker or delivery area, and you see that the aircraft aborted the mission correctly. So now you can sweep that space and make a lot of different games around the dog being closer, the dog not being a dog, being a child, being a horse, being a human, being sort of a cocktail party, whatever it is, and playing with the environment, and playing with the lighting, and playing with the wind, and playing with the sensor error, and you sweep the entire simulated space. And of course, what you can do is you can do a lot of diversity in testing, but they're not realistic. They don't really represent the real world. So you get a lot of scale, but you don't get a lot of accuracy. So you then bridge the two with synthetic data. This is in the real world, but simulated scenario. So here's a case of we just put a toy horse, which is sometimes heated to make sure it generates the right sort of bolometric signature, and we drive it into the delivery area and make sure that the sensors can see it and make the right decision. And obviously, sort of here's a real-world scenario where we take our sensor package and suspend it over an actual backyard, and sort of see that we can detect the people, the algorithms work correctly, right? And here are multiple different examples of the same thing. You can see that this is a pretty challenging example. Why did it go away? This is a pretty challenging example because the person was actually sitting on the car. The car is hot, right? So you need sort of a lot of you can't actually detect it easily. So the idea is you collect and generate a lot of diverse data. Some of them are high scale in the simulated world, and some of them are high accuracy in the real world. And then you bridge between the synthetic data. And you keep a validation set to the side. This is really important. You give a main set. The size difference of like how much do you keep on a side and how much you give your scientists, it's sort of up to you. It depends on the system. There isn't one right answer. But the engineers and scientists develop a developmental set. And when they give you a version of the system, you qualify it against a validation set that the algorithms and the scientists and engineers have never seen before. All the data is new. All the data is 0 day. This is really important. It means that you continuously have to generate new scenarios that are 0 day. Because once you've used that validation set, you cannot use it again. the system has already seen it. It doesn't actually give you any proof. And the only way you qualify a version of the system if it survived correctly with the alpha beta have reached the right probabilities, the right the sort of number of sigmas, to know that the system will behave correctly in the face of 0-day data. In other words, when the system will throw a completely random event that the system has never seen before, you'll have a high probability of safe outcome. And how high? Well, as high as the error that the system or the damage the system can generate, right? So if it's a benign error, then you don't need very high probabilities. But if it's actually a dangerous sort of outcome, then you need your statistics to be sort of very strong. And one of the things I do is, like, can you think about a completely known robotic version of the Swiss cheese heating? And there's one, I think, from about 4 years ago. This happens to be an Amazon one. But there's actually, I have a whole dictionary of these. I tend to collect them and keep them around. I use this one because it's so interesting, but it's purely a virtual cloud service, right? So this happened. And what I love, about this is the explanation, right? So Alexa woke up, were in the background that sounded like Alexa. It wasn't. Then it heard something that sounds like send message. It wasn't. At some point, select to whom, at which point the background conversation interpreted as a name in the customer contact list, right? There's a lot of layers here. Then it asked contact, right? And interpreted the background conversation as right. As unlikely as this string of events is, right? Okay, so this is a classic case of the Swiss cheese. And what you're actually seeing here is an incredibly strong engineering team that didn't calibrate the probabilities correctly, right? The outcome is actually pretty bad, right? It's the sort of a privacy violation. Only happened once, and the error was immediately corrected. And sort of, I know the team personally, and they actually sort of took responsibility and did a lot of work to make sure it never happened again, both for them and other parts of Amazon. But this is the Swiss cheese, the classic Swiss cheese hitting a completely online service. And potentially doing something that isn't benign. So I'd like you to think about it very deeply. The good outcome that as a result of this, I got to go speak about the Swiss cheese to every single principal engineer at Amazon, and all of them now know about it and think about it, engineer around it, and that's actually good, right? Whenever you take one of these failures and you convert it into a teaching moment, that's a very powerful thing. Okay, back to the $100 million at 22,000 miles per hour, Space IL. So here's what actually happened. So they have two INS systems that have to sort of be. It's enough to have one during the landing phase, but one of them actually reset and during the descent, and the human operator didn't actually know, because that wasn't documented. In other words, that's a currency and training gap, that if they reset that system, it's going to reboot both INS systems. And now the system actually has to reboot while it's flying, flying towards the moon, and you have no intrinsics or extrinsics at all. All they had to do is leave the system alone and not push anything, and the system will just land with one of the INS systems. But they try to reset it, which reset the second one, which put the system in a fail-safe mode. And by the time it rebooted, it hit the moon. Now, that's a classic human factors error, and this is something that I haven't spoken about a lot, but maybe early in the aerospace part. But we often underestimate the effect of humans on a system like this, right? Is the system able to be disturbed with a human factor error? Because humans, almost by definition, their error rates is pretty high, and especially when they're faced with a complex system and sort of time-constrained decision-making, the error rate is somewhere between 1 to 10%. If you look at a lot of the statistics out there around accidents, this is data that the NTSB actually maintains. I'll encourage you, if you're interested, to look at it. And I think it's really important. There's a wonderful lesson here that they did everything right, except that the human shouldn't have pushed the button. By the way, I've used this lesson in Prime Air, by the way, in this concept called the independently safe concept, where the system is allowed to reject operator guidance if it thinks it knows better. So let's say someone says, no, it's okay to keep flying, you're safe, and the system, through perception and SLAM or whatever it is, right? Diversity of sensors said, no, but there's a tree, there's a building, there's a construction crane, something that wasn't there before. it's allowed to reject that human instruction. And I think about this independent safety capability as a critical layer of the Swiss cheese that a lot of us forget to put into the system. Mostly because we tend to think about human supervision as being helpful, and often as the system gets more complex, the humans can introduce more errors that they can capture. And with this, I'll maybe shut up and we'll have a conversation about this. Thank you.
Thank you.
I'll jump in with one. I had a very specific question about the single engine versus dual engine and the failure modes, where single engine had a lower fatality rate. Do you have any sense whether that translates to autonomous flight as well? In other words, like, is the failure mode a pilot guiding the engine safely, the plane safely to the ground? Is there any insight there?
Yes. So if you had, and the difference between a sort of envelope protection and envelope limiting autopilot, if you have an envelope protection fly-by-wire system of the kind that you have in very, very modern jets, like Airbus 350. I mean, I think the 320 does this too, but I'm not sure how well. They'll self-trim to make sure that the aircraft will behave the same way from the pilot perspective. The issue with these systems is the pilot, the aircraft becomes sided. And all your instincts as a pilot, you've been trained to fly these nominal missions, and suddenly the aircraft changes its flight characteristics in a pretty drastic way. And often the accidents happen just as you're coming in for a landing, right at the end of the flight. Almost by definition, all of these errors will happen after the engine has been running for a long time. So they tend to concentrate at the final leg. And when they happen when you don't have time and your instincts take over and your brain doesn't really think about, like, okay, the airplane is different now. I have to change the way I fly it. A lot of pilots will make mistakes. And again, this is where the human ability to be contextually alert and change our models in our head just isn't robust enough for all of these systems. And of course, an autopilot or certain kinds of autopilots fly-by-wire systems can actually protect a system against this. And it's less about autonomy. There are airplanes who won't let the pilot do the sort of maneuvers in an engine-out situation that will cause the aircraft to go out of control. Unfortunately and unnecessarily, I think these technologies haven't really made it yet to general aviation. I really think they should. And you can make twins. Now the other reality is that there are twice as complex in a twin engine. So yes, I'm not going to talk about the chance of this happening, but you can simplistically say that the two things that can go wrong, the chance of them going wrong is twice as much. No, I know it's oversimplified, but it's probably higher than that because there are two maintenance points and two two failure modes, and left and right aren't actually perfectly symmetric in a lot of these piston airplanes. So that complexity can lead to these strange modes that are very hard to sort of understand what to do about, right? I mean, this is a classic control problem where you don't, you have your primary plant that you can control, and the plant has changed behind you, and now you either have a robust way to detect what a new plant is and apply a new control strategy that can, doesn't let the new plant go out, degrade. But this is sort of an interesting system theory problem. A lot of modern systems actually use beat controllers, and they don't use sort of model-based system theory control. And you have to have really good sensing around what mode you're in. And if you fail to detect the right mode, then you don't really know what control strategy to apply, and then you can fail. But it is solvable. I would say that, right? I mean, I definitely have solved it in Prime Air. And I know sort of Airbus and Boeing are solving it as we speak. It's unfortunately that inspiration didn't make it to the rest of the industry yet. I really think it should.
Is the dual versus single engine aircraft kind of idea like a bit of an example of Simpson's paradox, in the sense that single aircraft aircraft might crash more, but they're less fatal. So actually having a double engine aircraft which carries more passengers, if you switch them to be single engine, they'd actually increase fatalities. Like these two.
No, it's calibrated. It's actually the number are normalized for per passenger. They're not across passengers. So it's been normal. Like it's not because you carry more passengers. I actually picked two airplanes that are pretty similar in the passenger carrying capacity.
I see. So this is purely a human psychological bias that we feel safer with two engines.
We do. I have friends who fly airplanes, and here's the nice thing. There's a really simple way of explaining it. That the airplanes, when you lose your single engine airplane, you lose the engine. You still glide, but the airplane is symmetric, so you have no power, but the mechanics of flight are the same. So your instincts and your training, you don't have to change the way you fly.
Yeah.
So you just find an open field and you ditch, and most of the time you walk away from it. That happened to a friend of mine recently, actually. In a single engine airplane, he landed on a highway, waited for the police to come and tow him to the nearest airport, fixed the engine, and flew home. It was dramatic, but nobody was harmed, right? In a twin engine, when you lose that second engine, the dynamics of the aircraft change in a material way, and sometimes in an unpredictable way, depending what the failure is. So now the pilot has to stop operating the old way and start to operate this new off-nominal way that they don't practice very often. Like most of the practice is flying nominal missions, right? They maybe practice once a month or once every quarter or every 6 months. And now you sort of low currency, low training, and that even assumes that the failure is exactly what they practice. Often when you have damage, the failure isn't exactly the same. And you just don't have the time to go and figure out exactly what went wrong. And I'm not going to go into the details, but there are some really interesting airline accidents that are purely because the pilot didn't know that the aircraft was highly asymmetric after the failure. They just didn't have the right sensors on the airplane to tell them that as long as they make left-hand turns, they can re-level the airplane. But once they make a right-hand turn, they can't recover. The airplane will just spin out of control.
Right. I guess I find it hard to believe that. Well, I mean, empirically, all kind of modern aircraft that carry large numbers of passengers are twin engine aircrafts, right? So why is that?
It's way more fewer things to fail than a 4-engine aircraft, and the fuel efficiency is way higher. Less drag, better fuel efficiency, better performance, better nominal performance. You can climb faster. And it's actually the engines, the part that fails, which are the engines, fails less because the engines don't work as hard. And remember, I'm not comparing a 4-engine to a 2-engine. A 2-engine is better than a 3-engine, 4-engine with the right reliability of the engines every single way. I'm comparing a 2-engine to a single engine. That's a whole other thing.
Okay, so it's partly the size of the aircraft as well.
No, it has nothing to do with the size. It has to do with the functional capabilities of the fly-by-wire system and the what specific failure mode happens, and does the fly-by-wire system protect you from these failures to make sure that the pilots don't have to fly the airplane in a new way, and they do have enough perception to understand the new plant constraints and remain within these constraints. Because we know pilots just, that's very hard to figure out how to fly a plane that you've never flew before.
So,
right?
just so I'm following completely, there are commercial aircraft which have 2 engines, which could have a single engine, which don't currently, and are less safe but cheaper.
There are places where losing that primary engine is catastrophic, right? If you're over the ocean.
Okay, right.
So you don't really have a choice.
Right. So this is more of a.
So it's a functional descriptor, right?
It's a reporting bias in the types of accidents that are
exactly
mentioned, right? Rather than. Okay, that makes sense.
Yep. These are great questions, by the way.
Hi, Gore. I have a quick question for you. One observation, one question. You didn't mention Tesla, and the question is, do you think that these?
Are you going to talk about LiDAR? Why LiDAR?
I'm not qualified to talk about LiDAR. I hope maybe you are. But my question is, do you think that the systems that operate these machines, like Tesla cars or airplanes or these drones, do you think they should be susceptible to investigation by the operators to maybe have, I don't know, a virtual simulator of a Tesla car at home so that you can try out different things and kind of understand the failure modes yourself. Do you think that would be a good thing, or would that be more of a worse thing?
So first, let's talk about the regulatory environment, right? So aeroplanes, medical devices, telecommunications, and money are the four categories of third-party certification sort of products, right? So you can't just build a product and put it out in the market. You have to get third-party certified by whatever the sort of the authority, or the sort of the FAA in the case of airplanes, and the FDA in the case of medical devices and drugs, and FCC in the case of telecommunication equipment, etc. And interestingly, automotive isn't. Automotive is a first-party regulatory environment where there are rules and regulations that are put in place by the DOT or whatever the local equivalent is, and you have to qualify against and test against them, but you self-qualify. You don't get tested by the regulator. And you only get tested when you actually have an accident or an incident and the NTSB comes in. And the NTSB at that point can go and ask you whatever question you want and do recalls. I mean, famously, the Toyota acceleration issue, if you look at it, that was a classic case where the bug was there for a long time, and they just found it after a lot of accidents. And then that's an interesting incident investigation if you're interested. And I tend to read a lot of NTSB reports because it gives you this interesting point of view on what kind of failures are out there and how people are working around them. Now, talking specifically around self-driving cars, I think, obviously, I'm not saying anything you guys don't know, but there are two sort of approaches to self-driving cars. One is the sort of the slowly increase the safety systems, the active safety system in the car, so the people are protected, but the driver is still the driver, right? I mean, it's more sort of envelope protection kind of a thing. It's a automated brake when I'm backing up if there's something behind me kind of a system. And that's very different than a self-driving car. And I think it's a great a car that can't hit anything with high certainty. I think is way more useful right now than a self-driving car, to be completely honest. I'm not against self-driving cars. I think they'll happen in the future, but I think they're sort of they're much further out than people think they are to work in every scenario. Now, if you do if you close down a lane on a highway and say this lane is only for self-driving cars and you can only engage the system while you're on that lane, sure, that's doable, maybe right now, almost, right? But you talk about a car that can handle any environment in any weather situation, and the driver can just lie down like the passenger at this point is in the back sleeping, I just don't buy it. And the issue is like, okay, so now let's talk about diversity, right? I assume you say Tesla mostly because they don't like LiDARs and they speak about it all the time. There are a few other companies who are trying to build vision only or no LiDAR self-driving capabilities, and there are really two stories. One is there's a perception that we are driving cars as humans and we don't have LiDARs, right? We don't have radars and sonars and long wave IR sensors and time of flight, and we just have our eyes, like V1, perception system, Mark 1 perception system. And we seem to be doing just fine as drivers, and the reality is we are not, right? Driving is incredibly dangerous. It's one of the most dangerous things we can do. And tens of thousands of people die every year, hundreds of thousands get injured every year in the US, and millions die every year around the world or injured. I mean, the numbers are pretty bad. So just saying, well, there's an anthropologic sort of proxy here, like humans can do it and we only have vision, therefore vision can do it, I think is problematic. I'm not actually saying that you can't only do it only with vision. I'm aware of at least one company who's trying extremely hard, that's not Tesla, to do it just with vision. And I think their approach is interesting, and they are, they're challenging themselves to sort of reach very high levels of safety. And if they're successful, then of course they have a much simpler system, right? Like a system that's made just of cameras. It's just intrinsically simpler than a system that has a lot of diversity in both algorithmic diversity and sensor diversity. And some of the arguments you can make are also the simplex versus complex. That's why I introduced the idea of a single engine and twin engine, because it's not always the case that a system that has diversity is safer. you have to sort of just think about every failure branch in the failure tree and how it can propagate and how you can contain it. It's a lot more complex than that. And yeah, so I mean, I think, okay, now LiDARs very specifically, I think LiDARs have a wonderful property of direct measurement, time of flight. That's great, but I think they're still a photonic sensor. So a failure mode that can impact cameras can easily also impact LiDARs. And that common failure exposure for me is problematic. So if you have cameras and LiDARs, I'll ask, okay, do you also have radars, right? Because at least you have some other modality that will fail in a completely different way. I think that'll be my question. I'm not against LiDARs in any way. I think like, I think a simplex versus multiplex, like a complex system, just it's different. You have to engineer it differently, and you can reach high levels of safety. You just have to be very disciplined about how you model all the side effects, and you have the closed form solution that with the right sort of margin of safety, probability is outcome, and sort of etc. Right? I mean, there's no one simple answer here.
And do you think it's valuable to have a system like that open source, so to speak, or available for inspection?
I think it's more gamification than inspection. I don't like. I like the idea of exposing some of these systems in a simulation to a lot of end users, because I think they'll exercise the system in a unique way that maybe the system has never been tested before. So it's more about scalability and diversity in simulation and test cases. I think that is interesting. I think in terms of our ability to sort of interact with the system and find the edge cases, no system that's actually well designed. I mean, unless you do some really complex sort of Monte Carlo, blah, 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 sweep of all the parameters, it's going to be pretty hard to find the crunchy corners. And if you can easily find them, then, the system really is, it's a demo, it's a prototype, it's not a product. At least in my experience. I'm not against it. I think it's more of a gamification of the high scale testing strategy. I think that's actually super interesting.
Thank you, and thank you for a great talk.
Yeah. No, thank you.